Welcome to day 10 of Unit 6. We got homework that's in the textbook. These are each your answers, but we're actually going to go through each of the questions one by one, so you'll be able to check your answers as we go. So for the first one, we've got an improper integral based on that top bound, so we'll do limit as b approaches infinity, integral 1 to b of our expression. Do your antiderivative of that, you get really negative x to the negative 1, which becomes negative 1 over x. Sub in your b, and then you got minus a minus when you sub in the 1, so you get plus 1. When b approaches infinity, that denominator becomes huge, so the value of that fraction approaches 0. 0 plus 1 is 1, so therefore this is a converges. Number 12. Our improper part is again that top bound, the infinity, so limit as b approaches infinity. Integral from 1 to b, I rewrote the expression as 4 times x to the negative 1/4. Exponent goes up 1, so we now have 3/4. Divide out front by 3/4, which is the same as multiplying by 4/3. Sub in your b, sub in your 1. As b goes to infinity, that first term goes to infinity. So because we have an infinity involved, in that case, it's infinity minus some number, so it'll still be an infinity. Anytime there's an infinity involved, it's automatically a divergence. Over in 19, this is a little u substitution. So we got to let u equal the natural log x, so du is 1 over x dx. So that ends up as just a u to the negative third. I redefine my bounds. Rather than being 4 to b, it's now natural log of 4 to natural log of b based on our value of u. Antiderivative of u to the negative third, you got u to the negative second with a minus 1/2 out front, and I just brought that u to the negative second down to the denominator. Fill in my natural log of b, fill in my natural log of 4. That graph of natural log looks something like that. So as b goes to infinity, natural log of b also goes to infinity. So essentially our denominator is getting huge in that first term. When the denominator gets huge, the value of the fraction goes to 0. So we're just left with that second part. So we are converging at 1 over 2 natural log of 4 being squared. For 20, we got pretty much the same u substitution. We'll let u equal natural log x, so the du is 1 over x dx. Limit as b goes to infinity. Redefine our bounds. Instead of 1 to b, when you sub them into the ln of x, we get 0 to natural log of b. Antiderivative, we get 1/2 u squared. Fill in the natural log of b and the 0. Natural log we saw as b goes to infinity will go to infinity itself, so that's just an infinity, and we get a divergence. In 21, there was 2 ways to do this. So because we had bounds of negative infinity and infinity, you had to pick some number in the middle to split it up. I chose to split it up at 0 because that I thought would be pretty easy. Now because 2 over x, 4 plus x squared is an even function, you could have just done the 0 to infinity and then doubled your value. That's an option. I showed it here as doing the negative infinity to 0 and 0 to infinity separately. But again, you could have doubled it because it was an even function. So that's an arctan there. After I did my limits, I have a approaches negative infinity, b approaches positive infinity in the second limit. So that's an arctan there. Pulled the 2 out front. The 4 is really a 2 squared, so 2 goes in the denominator out front and denominator inside. So really it just ends up as arctan x over 2. So I filled in the 0, arctan of 0 is 0, and then you have the arctan of a over 2. Similar idea on the other side with the b and the 0. The graph of arctan looks like that below. So as a is going to negative infinity, the arctan is going to negative pi over 2. So that's how we get the minus negative pi over 2. And then as b goes to positive infinity, arctan's going to positive pi over 2. So you're just adding 2 pi over 2's together, so you get it's converging at pi. For 25, limit as b approaches to infinity. Our issue was on the top there. Antiderivative of sine of cos is sine, and we got a little correction of 1 over pi. It's technically a u substitution, but we've seen corrections like that a bunch, so I chose not to show it. If you had trouble doing that, then you might want to do the u substitution. Fill in your b, fill in your 0. Sine of 0 is just 0. Well, as b goes to infinity, sine is not going to approach anything. It's going to bounce back and forth. So because it does never actually approaches something, this is a diverges. And 70, which had 3 parts, we've seen questions like this before that have you do area, spin it around the x-axis, and then spin it around the y-axis. So area, we're in dx, so we're doing integral of top minus bottom. So the region started at 1 for the x's and goes to infinity, which makes it an improper integral. So do your limit as b approaches infinity. Antiderivative, when the exponent goes up 1, we're at an exponent of -1, divided out front by -1, so really we have -1 over x. Sub in the b, sub in the 1, the minus makes it a +1 really. As b goes to infinity, the denominator gets huge, meaning the fraction goes to 0, so this is converging to 1. For the second one, we're going over the x-axis. The region is completely resting against the x-axis, so this is disks. So we have the setup of pi radius squared. So here's an example of one of our disks. That little bit there's our radius, so it's a top minus a bottom. So it's just function minus 0. So the 1 over x squared is getting squared to give us 1 over x to the 4th. That's really x to the -4, so we just do a quick antiderivative. So we have -1/3 x to the -3, and I brought that back down to the bottom as an x cubed. Sub in your b, sub in your 1. As b goes to infinity, that denominator gets huge, so the fraction goes to 0. So we end up just having pi over 3 for our volume. And then when we go over the y-axis, I did it with shells. So our shell is looking something like that. So the height is top minus bottom is just a function. That's where the 1 over x squared is coming from. And then the radius, if you do a right minus a left, it's a random value of x where I drew the slice, minus 0. So that's why the radius is just x. Multiply those together to get 1 over x. We do get natural log absolute value of x for the antiderivative. Sub in your b, sub in your 0. Well, as b gets huge, natural log gets huge, that goes to infinity. Therefore, it diverges. All of these, make sure you cannot do your antiderivative and everything with the thing that's making it improper. So in this case, it was usually an infinity. You do need to rewrite it as a limit before you go ahead and do your antiderivatives. All right, so we're going to go to day 10 in the notes packet. It says from the other day, and I'm going to assume that we did not do this problem the other day, so we're going to go ahead and work through it. So we're going to spin the region under our curve about the x-axis. Well, what we want to recognize is that it is symmetrical about the y-axis. So what we're going to do is we're really going to just spin this region around the x-axis, and then we will double it. So our bounds of that region are 0, and then it goes forever, so it goes to infinity. So I'm going to have 2 times the integral from 0 to infinity. We're going to have a disks, so I'm going to throw the pi out in front. So just keep in mind the 2 is because we had 2 parts, the left and the right, and then we have the pi from disks. So then we'll have some radius squared, dx. As we spin this around, our disks will look like that. So our radius is a top minus a bottom. So it's just function minus 0. So we have 1 over square root of x squared plus 1. We need to rewrite this as a limit because it's an improper integral. So we're going to have limit as b approaches infinity. We'll have 2 pi integral 0 to b. When we square this out, this becomes 1 over x squared plus 1 dx. Well, this is just our basic arctan. So this becomes limit b approaches infinity. We've got 2 pi arctan x evaluated from 0 to b. So limit b approaches infinity, it's going to be 2 pi. We'll have arc tan of b minus arctan of 0 is just 0. We had it on our homework one slide, but remember this is going to pi over 2 when we go to infinity, and negative pi over 2 when we go to negative infinity. So as that b approaches infinity, that first term is just going to be pi over 2. So we'll have 2 pi times pi over 2, which will eventually give us pi squared. So this volume will be bounded. It will converge to a volume of pi squared. If we had an infinity involved at all in our answer, then we would say that it diverged. All right, going down to the next one. Essentially, this is 1 over x. Well, 1 over x has issues when x is equal to 0, which is in our interval. So what we're going to have to do is we're going to have to break this up into 2 integrals. We're going to split it at 0 because that's where the problem is. So we'll have negative 2 to 0, 1 over x dx, plus integral from 0 to 2 of 1 over x dx. So this first one, on the interval negative 2 to 0, this is like this part of the graph, we're approaching 0 from the left. So we're going to do limit as b approaches 0 from the left. And we're going to have the integral of negative 2 to b of 1 over x dx, plus, for the other one, like in there, we're approaching 0 from the right. So we're going to have limit as a approaches 0 from the right, integral a to 2 1 over x dx. So this becomes limit b approaches 0 from the left. This is going to be natural log absolute value of x, evaluated from negative 2 to b, plus limit a approaches 0 from the right, natural log absolute value of x. We're going from a to 2 in that case. So this will be limit b approaches 0 from the left. We're going to have natural log absolute value of b minus. If you sub in a negative 2 and then take the natural log, we're going to have natural log of 2 plus. Now we'll do our other limit. We'll have limit a approaches 0 from the right. This will be natural log of 2 after we take the absolute value, minus natural log absolute value of a. Well, the minus natural log of 2 and the positive natural log of 2, those will end up wiping out. Here's our graph, roughly, of natural log. So b numbers are actually negative, but because they're going to be taking the absolute value, they'll be positive. So essentially, we're just heading towards 0 from the right for this blue limit for the natural log. So that's going to go down to negative infinity. These wiped out, and as a approaches 0, that's going to go to negative infinity as well. So we'll have minus a negative infinity. Now this is not 0. We saw in day 8.5 that infinity minus infinities can be lots of different things. If you have any infinity in your final answer of an improper integral, it is automatically a diverges. An improper integral only converges if there are no infinities in your final answer, and therefore it's converging to some finite number. If there are infinities involved at all in your final answer, it is automatically a diverges. So the next 2 pages we're going to skip because we talked about that on day 8.5. And we're going to go over to the one that has our integral from -5 to 0. Now the issue we have with this on the interval -5 to 0 is just the 0. As we see from the graph there, there will be an asymptote at 0. So we're going to have limit as b approaches 0. And if we're going -5 to 0, it's looking like this. So we're approaching 0 from the left. We're going to have integral -5 to b. I'm going to write this as 1 over x cubed dx. So this is limit b approaches 0 from the left. This is really x to the -3. So the exponent is going to become a -2. Divide out front, you'll have a -1/2. And I'm going to write that x to the -2 as 1 over x squared. And this will get evaluated from -5 to b. Well, this is going to become limit as b approaches 0 from the left. This is -1 over 2b squared. And it'll be plus, so we sub the -5 in for x, we'll get 25 times 2, so plus 1 over 50. When we sub tiny negatives in for b, it's going to get squared, so we're going to have tiny positives. So this is going to be -1 over some super tiny positive. So think of it as like 1 over 10,000 or so. If you do -1 divided by 1 over 10,000, that's really -1 times 10,000. So this is going to end up giving us a big negative number. So in other words, that first term is going to go to -infinity. If you've got a infinity involved at all, this is automatically a diverges. So one of the things highlighting today is improper integrals are a little bit harder to recognize when it's not an infinity in the bound. So you need to think about, are there things that are in the interval of our bounds that are making it undefined? Sometimes that could be one of the endpoints, sometimes it could be a value in between. In this particular one, we've got an infinity there, so we know it's got to be improper. Notice also, though, that 1 makes it undefined. So we have issues on both ends. So how you treat this is you pick some convenient number in between. So I'm just going to pick 2. So we're going to do the integral from 1 to 2. And I'm going to rewrite this as 1 over cubed root of x minus 1 dx, plus the integral from 1 to infinity of 1 over cubed root of x minus 1 dx. And each of these will end up getting their own limit. So in the first one, we're doing basically that part. So we're approaching 1 from the right side. So we're going to have limit as a approaches 1 from the right, integral of a to 2 of 1 over cubed root x minus 1 dx. For the other one, I made a mistake on this second integral. Sorry, we need to fix that. We were splitting it up at 2. So this bottom bound on the second integral should be a 2, not an infinity. Sorry about that. So this is going to be plus the limit as b approaches infinity. We're going to have integral 2 to b of 1 over cubed root of x minus 1 dx. So we technically have a little u substitution here. So I'm going to go ahead and let u equal x minus 1. Du is going to equal just dx though. So we're going to have limit a approaches 1 from the right. If we put the 2 into our x minus 1, we're going to get 1. and we'll have a minus 1 on the bottom. This is going to be 1 over cubed root of u, which I'm just going to write as u to the negative 1/3 du. And we'll have a similar idea over here with changing the bounds and everything. So the 2 will become a 1, and we'll have b minus 1 here. We'll have u to the negative 1/3 du. So we now have limit a approaches 1 from the right. We'll have u to the 2/3 with a 3/2 out front. That's going to get evaluated from a minus 1 to 1. Plus limit b approaches infinity. We'll have the same thing, 3/2 u to the 2/3. And we're going from 1 to b minus 1. We'll sub those things in. We got limit a approaches 1 from the right. That's going to give us 3/2 minus 3/2 a minus 1 to the 2/3 plus limit b approaches infinity, 3/2 b minus 1 to the 2/3 minus, when you sub in the 1, we'll just get 3/2. So we'll have 3/2. As a gets close to 1, that second expression is going to go to 0. So we'll have 3/2 plus 0 plus. As b goes to infinity, that first expression is going to infinity, and then we have a minus 3/2. Because there is an infinity involved, this is automatically a divergence. Okay, essentially it would end up as infinity. All right, 2 more we're going to look at. So we've got natural log of x, we're going 0 to 1. So the problem here is the 0. So we're going to write this as limit as a approaches 0 from the right, integral from a to 1 natural log of x dx. Well, we don't have an antiderivative for natural log dx. This is something we've seen a couple times using integration by parts. So our first thing in the hierarchy for our u's for integration by parts is natural logs. So we'll let that be our u, meaning dv is just dx. V will be x, and du will be 1 over x dx. So this becomes limit a approaches 0 from the right. Our uv will have x natural log of x minus the integral of v du. The x times 1 over x wipe out, so we just have dx, and this is still a to 1. Remember, in a definite integral, we don't evaluate until we've resolved all integrals. So this becomes limit a approaches 0 from the right, x natural log of x minus x, and we're going to evaluate it from a to 1. So that's limit a approaches 0 from the right. When we sub in the 1, it's going to be 1 times natural log of 1, but natural log of 1 is 0, so we'll just have 0 in that spot. Minus 1 when we sub it in for the x, minus start a parenthesis. We're going to have a times natural log of a, and then we're going to have minus a. So we'll have 0 minus 1. This is going to be a 0 here, and then this is going to be times a negative infinity. And then this will be minus a 0 for that part. So a 0 times any type of infinity is an indeterminate form. So we need to actually take that off to the side. So we've got limit a approaches 0 from the right. Our technique when you had a 0 times any type of infinity is you moved 1 to the bottom. Well, that a can be more easily moved to the bottom than the natural log of a. So I'm going to leave natural log of a on top, and we'll write this as 1 over a on the bottom. We saw that this was negative infinity. Well, as a approaches 0, this is going to be a tiny positive. So think of the 1 over a as 1 over like 1 over 1,000. If you do a keep change flip for that, that whole thing will end up as a big positive. So this is really negative infinity over infinity, which leads us to a L'Hopital's. So we'll have limit a approaches 0 from the right. We'll do derivative of the numerator on its own, derivative of the denominator on its own. Natural log of a's derivative is 1 over a. 1 over a is really a to the negative 1. So when you do a to the negative 1's derivative, that should be negative 1 a to the negative 2. And I'm going to write that as negative 1 over a squared. Well, 1 over a divided by negative 1 over a squared is 1 over a times negative a squared over 1. One of the a's wipes out, so we just get negative a. So this really becomes limit as a approaches 0 from the right of negative a. So therefore, this is just going to approach 0. So if at any point you have a 0 times an infinity, you can't just say what that's going to be, because it could be either depending on the parts of the expression. You've got to go off to the side and do a L'Hopital's. So we now know that this is 0 minus 1 minus the ALNA is 0 minus 0. So this is just going to approach negative 1. All right, for our last one, we're looking at secant on 0 to pi over 2, which is like that there. So the problem is the pi over 2. So we're going to do limit as b approaches pi over 2 from the left. So this will become integral 0 to b of secant theta d theta. Secant's antiderivative is one that we know. So this is limit b approaches pi over 2 from the left. We'll have natural log absolute value of secant theta plus tan theta, and that'll get evaluated from 0 to b. So we'll sub in our b and our 0. So we've got limit b approaches pi over 2. Natural log absolute value, we've got secant b plus tan b minus natural log. So we've got the graph of secant right there. Secant of 0 is just 1. Plus tan of 0, which is sine 0 over cos 0. Sine of 0 is 0, cos 0 is 1, so 0 over 1 is just 0. So inside that second natural log, we'll just have 1. Natural log of 1 is 0. So that second natural log is going to be completely gone. So as secant approaches pi over 2 from, oops, I forgot my left right there, from the left, notice the secant graph is heading upwards. So this is going to be an infinity here. Tangent's graph I'm going to draw right on top of here. Tangent's graph looks like that. Tangent's also going to infinity. So natural log of huge numbers, natural log's graph looks like that, is also going to approach infinity. So this, therefore, this diverges. So the big thing about today is just gotta look at each integral now and just be cautious if something within the bounds is going to make it undefined, because it may not always be an endpoint value, and so therefore you might not see like an infinity on the bounds. It could be something within the interval that makes it improper. Any time left in the period, you can be working on your homework, or you can work on your review sheet for the exam. Have a great rest of your day.